Alrighty, lovely, good. So we're going live. What is up, everybody, and welcome to Data on Kubernetes Communities live stream number 103. Very happy to be here as always. To give a little bit of context, if you have not seen the Data on Kubernetes community report, you definitely need to take a look. I'm going to drop the link here in the chat so you can take a look at that. And why is that important? Because when our community got started last year in July, the central focus was on databases and storage. But obviously, the Data on Kubernetes landscape is much bigger than that. And one of the things that's very important to keep in mind if we're talking about Data on Kubernetes is the use of big data technologies, bringing on things such as analytics onto the scene. And you'll see a lot of those things mentioned in the research report that I've left here in the YouTube chat. Now, very happy to introduce our speaker today. Not the first time we've had someone from his wonderful company, Treeverse. His name is Itai Admi, and he's based in Tel Aviv, and he's the R&D leader at Treeverse. Itai, welcome to the Data on Kubernetes community. Could you just give us a little bit of background about yourself and how you got started out with analytics, Kubernetes, Spark, LakeFS? How did this all happen?
Okay, so hello everyone, and thanks Bart and the DoK community for having me. I think I started experimenting with Kubernetes when I left Microsoft in 2018. I joined a small startup company named Ridge, and in Ridge we built a distributed cloud, which basically means that we got partnerships from various data centers, and we built our web services on top of them. And there I was in charge of building the Kubernetes managed service. So I was eventually quite familiar with everything that has to do with cloud providers and spinning up Kubernetes with kubeadms, the kubelet, and networking and volume. So it was a very cool experience to manage and build Kubernetes on top of various data centers.
Okay. And what is it that we're going to be talking about today?
So today we're going to talk about performant and version-aware analytics with Spark and LakeFS. I know the title might be a little bit surprising because when we think about performance and we think about versioning, they kind of sound conflicting to us. It feels like we need to give one of the two, maybe to pay a little bit on our performance when we have versioning. And we're going to see how we build LakeFS to kind of have both.
Okay. All right. That being said, if you want to start sharing your screen, go for it. For folks that are in the audience, remember, please feel free to leave your questions in the chat while we're talking. We will get to them accordingly. If for whatever reason we don't have enough time, we can definitely continue the conversation in Slack. So Itai, whenever you're ready, you can take it away.
So can you see my screen now?
Yep, perfect.
Cool. So as Bart introduced me, I'm Itai. I'm an R&D team leader at Treeverse, which is the company behind LakeFS. And today agenda is that we're going to talk briefly about data lakes, and I'm going to present LakeFS and how you could manage your data lake more reliably with LakeFS, and show you some of the benefits when using Spark and LakeFS, and we'll see a demo on top of Kubernetes. So first of all, let's start a little bit with some background about data lake and data lake architecture. The whole premise of a data lake is that I have this one place, which is a centralized repository inside my organization, where all the data sources can write to, and all query and process engines can read or do some queries, and everyone speaks the same language. So for instance, I could write files to S3 and then read them later on, or spill Parquet files to my Kafka topic and inside the lake, and then read them with Spark or in a Presto query. And all of this works because the lowest common denominator is just flat files and S3 API. The advantages of a data lake is that it's really scalable and cost effective. It's accessible with many application ecosystems supporting it, and it has a high throughput. But it also has some disadvantages. So it has sort of a huge repository, which is actually a huge shared folder. Now, it's a shared folder where all your objects are stored, it makes it really hard to experiment with the data. There's no easy way to reproduce the data that existed in some point in time. And also, how would you enforce certain properties of your data inside your lake, like allowing only a specific file format? We see many data lakes where it's impossible to make these guarantees, or they are defined as data quality checks that run over your data, which is already in production. So this is exactly why we've built LakeFS, and it is to help you to manage your data the same way you manage your code. If I had to explain what LakeFS is in just one sentence, I would say it's an open source atomic version data lake on top of your existing object store. What LakeFS does is to power your object store with capabilities that we believe are missing from the object store for it to be a good data lake. And those missing capabilities are mostly around versioning or data versioning. The idea of LakeFS is to provide a layer that sits somewhere between the object store itself and the tools you use in your organization. And it acts as a layer of manageability and reliability. This could work with any application that currently communicating with your object store. You could do the same trick and integrate any S3 compatible tool your data lake stack has today. And you will need to just set your S3 endpoint to your LakeFS installation and have your code point to the branch of LakeFS that you want to execute your code on. So let's quickly go see how this works. So we expose an API, which is a superset of the Amazon S3 API. So if you have an application that knows how to communicate with S3, you can also communicate with LakeFS. It's sort of it's transparent to your application. For example, if you have a Spark job that reads and writes, let's say, Delta logs files from S3 directly, all you have to do is change the endpoint from S3 to your LakeFS installation and keep working as usual. And LakeFS does all the magic in between. Later on in the demo, we'll see an example of that. Our API is compatible with S3, but we also added the functionality that we think are missing, and that's the versioning aspect using the Git terminology. So LakeFS makes S3 behave like a giant Git repository. I can create branches, commit, do merges between the branches, roll back to a certain point in time, or simply time travel and see different versions of my data. And in short, like all the powerful primitives that Git provides with code are now available on top of your data lake. So although LakeFS lets you manage data the way you manage code, bear in mind that code and data are different, especially when it comes to scale. Our goal is to give the same Git-like experience, but having it scale to multiple petabytes of data and billions of objects, and do it as transparent as we can comparing to your existing S3 or object store. We want you to be able to do everything you did before, but have those Git capabilities as well. So today we'll focus more about working with Spark and LakeFS. I'm sure that most of you are familiar with Spark, so I'll just introduce it briefly. It is still the most widely used engine for scalable computing. It has great ecosystem for data science, for analytics, or other infrastructure tools, and it has development APIs in many languages like Scala or Python. Going through the architecture very shortly, there are many different distributions of Sparks, but they all look kind of the same. You have your master node. Inside of it, you have your driver program, which kind of drives your application. And the driver program can be anything like your Spark shell, for example. So the driver creates that context, which is the facet to all the Spark operation. And the cluster manager manages the job and basically separate it into tasks to be executed by the worker nodes, each existing on different node or VMs or pods, depends on your architecture. So the use cases are basically separated into three categories. You have your development environment where you want to safely experiment in isolation. You have the deployment where you want to avoid cascading data quality issues. We won't go deeply into that today, but LakeFS has CI/CD capabilities, much like GitHub, where you can enforce best practices to your data lake while you try to commit or merge to a branch. In production, you want quick error resolution. You want to recover from failures and identify the root cause. And by such, decrease the cost of mistakes and reproduce data issues in your own time with the LakeFS versioning. So as I said, in development, it is the easiest place to start, and it is something that we normally see LakeFS users struggling with their current architecture. So how do organizations achieve development in isolation today? They're either trying to copy their entire lake to another parallel universe where you work in isolation, but this is somewhat very expensive and hard to maintain. Or they copy just some of the data, which is also hard to maintain, and there's always something missing and you'll always be lagging behind production. And what they end up doing is not trusting this environment well enough. So using something like Git that offers you all those isolation guarantees on top of real production data with the same scale and characteristics is a very powerful guarantee. Now you can trust your development environment without paying the cost of copying the data or managing it yourself. So let's see how we experiment with LakeFS. You don't need to copy data around anymore because once you created your own branch, you know that it's frozen in time. And until you decide to update it, which you'll do by merging the master branch back into your branch or committing data to it, it will remain frozen until someone touched that. You also work in isolation. You know that no one else is going to be touching your data. And on the other hand, no production consumer of production data is going to read the data from your side branch. This is where the performance kicks in. Creating a branch is a very cheap operation, and you can decide to create new branches for each version of the experiment you're running. Maybe tuning a parameter of your model, or trying a different algorithm, or even changing part of your infrastructure, like testing a new version of Spark. Those could all be done in isolation, in a unique branch, and can be later merged into your production branch or simply deleted. So I'll cover deployment use case briefly. We won't go deep into any one of these. The case with deploying data is that every day we introduce new data to the lake. And even if the code and the infrastructure doesn't change, the data might. And the changes you introduce could have potential quality issues. So for example, if I'm using some client that sends me website event and there is a bug in that client, some data might get into my lake, not as a result of my change, but as a result of the client change. And this is one of the biggest complexities of a data product. The data we consume changes very frequently. So what LakeFS does is that it enables you to create a CI/CD inspired workflows to help validate expectation and assumptions about your data before it goes into your production. So you could safely make changes to your data by ingesting new data in isolation. And you could also enforce best practices like objects file formats. And if you think about it, it is similar to the code verification that we have today with GitHub, and our CI/CD workflows is inspired by that. Now the production use case. So in production, which is the most crucial part of any data pipeline system, sometimes errors occur. And when this happens, the best thing you can do is recover from it as quickly as possible. You can now roll back changes down to your lake using the LakeFS revert operation. And you can troubleshoot production errors more reliably by simply using the snapshot of the actual data when the error occurred. And you could also get some course collection consistency when you want to interact with more than one collection. So let's talk about reproducibility of errors. So for reproducing a state or a run of your data application, you need to have versions of both your code, your infrastructure, and your data. The code, which is running the job, let's say a Jupyter notebook running Spark. So the code version is probably managed by Git. And today it's easy to get to any point in time and execute the same code again. If we talk about infrastructure, where tools like Terraform emerged in the recent years and helped us manage our infra the same way that we are managing our code. So both the infrastructure or the environment could be also reproduced using the same tools. And when we talk about data, this is where LakeFS kicks in, and you could have a version control for your data lake with LakeFS. So using all three, you can reproduce your job, which becomes a combination of your ETL script or any code that you're running with your infrastructure, which is Kubernetes, and the data that you can retrieve from LakeFS. So reproducing a bug in production, let's say you upgraded Spark and deployed changes in production, and a few days later, you identified data quality issues or a performance degradation or some increase to your infra cost. And it is something that requires investigation and a fix. So LakeFS allows you to open a branch of your lake from the specific merge or commit that introduced the changes to production. And if we use the LakeFS metadata correctly, the metadata that was saved on the merge or commit, we can use that and reproduce all the aspects of the environment, like the infrastructure or the code. And then we can reproduce the issue on that branch and debug it. Meanwhile, our production data may be reverted to a previous point in time where we know that everything worked, or just keep it as it is. It all depends on your use case. So the LakeFS architecture, we'll talk about it briefly. If you want to read more about it, I'll share the info to our docs after the talk. So the way it works is that LakeFS exposes what we call the S3 gateway. And this is what my application is communicating with. And as I mentioned earlier, this is transparent to the application. Or with Spark, we can use the native LakeFS Hadoop client, which write the data directly to S3, while only writing the versioning metadata to LakeFS. So the S3 gateway speak the same speak with what we call the metadata manager that handles all the commit behind the scenes. And this commit, while they look like Git commits, their data model is somewhat different. And in our docs, I won't cover this today, but in our docs, you could also read about the commits data model. Here relies also an interesting story about how the Hadoop client developed. As we started just with the LakeFS S3 gateway, and we released that. And after some time, we started hearing feedback from the community saying that they don't want their entire data to pass through LakeFS. You have S3, which has an amazing throughput, and you don't want to scale LakeFS the same way that S3 scales. So we heard that feedback, and we developed the LakeFS Hadoop client, which allows you to write the data directly to S3 while only writing the versioning metadata, which is much smaller than that, to LakeFS. So deploying, here we have an example of how you could deploy LakeFS on Kubernetes. So LakeFS servers are stateless, which means that you can scale LakeFS as needed, and we know how easy it is with Kubernetes. The LakeFS state is kept both in the object store, where the committed data relies, the committed metadata, and in Postgres or an RDS server for references like branch or commit pointers. Depending on the amount of data your job is processing, you can also increase the number of Spark workers accordingly, just as you would with LakeFS. And the example that I manifested here, both the object store and Postgres database are managed elsewhere. You could also manage the Postgres yourself and deploy it in your cluster. But you can also deploy MinIO in your cluster, which becomes your on-prem object store, which LakeFS also support. And doing such, you could basically manage everything in your Kubernetes deployment. So here I illustrated how Spark will interact with LakeFS if it's deployed in the same cluster. With the LakeFS Hadoop client, data will be written directly by Spark to the object store, and the versioning capabilities are derived from the metadata, which is written to LakeFS. So the only change you will see is that you need in your the only change you will see to your Spark script is that you need to interact with LakeFS in the context of a branch. As you would normally just have the bucket and the prefix, now you need to add the branch itself. So here we have two examples. If you're using the gateway, you'll simply add the branch and add the appropriate LakeFS endpoint and credentials. If you're using the LakeFS Hadoop client or Hadoop file system, then the scheme changes from S3 to LakeFS and the branch is added as well. So here's an example. We'll also see a live one. You can do all of the changes in isolation and the branches will be available to you at any point in time. You simply change the branch prefix in the code that interacts with LakeFS, and you get different results on each branch. You can then read the result from each branch for every change you introduce and compare them. And you can also test how other jobs are affected by the changes by pointing them to the branch of your like. So again, there are two options to interact with LakeFS, and the first one is the gateway. Here we have two experiments running in parallel. We first configured our S3A Hadoop driver to communicate with S3, and then using Spark to do some aggregation. I can then compare the results of the two branches and do whatever I want with the results, delete any branch or merge them back into my production. The second option is to use the LakeFS Hadoop client, as I've mentioned before. When the LakeFS jar is loaded correctly, it will be registered for the LakeFS scheme. And reading or writing from LakeFS is done just as you would directly from S3, but with the branch prefix. So the metadata, as I mentioned, is managed by LakeFS, and we use it for the versioning semantics. The data itself is read directly from the object store. So I have prepared the demo. Let's see if I could. Okay, so I have a Kubernetes cluster, which I have nothing that is running on top of it. Let's increase the font a bit. And I have my LakeFS values, which is the configuration needed for installing the LakeFS Helm chart. I also have the LakeFS secrets, which hold all the secret information I need for running a LakeFS, like the S3 credentials and the RDS connection string, or some encryption key for my database. So let's go ahead and install the LakeFS Helm chart. It'll take a couple of seconds. Cool. So I haven't prepared any load balancers. This Kubernetes cluster is running on AWS and it will take several minutes. We'll do a dirty port forwarding trick and expose it. Let's expose this port instead. Cool. So now my local host will display our LakeFS cluster. We'll cover this soon, but first, let's also install Bitnami Helm chart, which installs one Spark master and two Spark workers, and then we'll configure them to work with LakeFS. So I prepared a couple of repositories. They're both storing data on S3. For the demo, I've already added a collection, a Shopify collection in my main branch. So I have just a single branch currently in LakeFS. It has two commits, the first one where the repository was created and the Shopify collection. And I have no uncommitted changes in the moment. So let's go and do an experiment in isolation. Let's create the daily ETL branch that is spins up, is created for my main branch. It has exactly the same data. And let's see if Spark already finished. Cool. So all of my pods are running. Now I will log into my master node and run some shell there to execute some script to run on top of, to store and to read and write data from LakeFS. Cool. And now let's go and start our Spark shell. let's go over this configuration quickly. So I'm starting my Spark shell with a couple of configuration. I need to configure the S3A driver credential, which is the access key and the secret key. And I also need to configure my S3A endpoint to talk to LakeFS, which is the pod running LakeFS inside my Kubernetes cluster. Okay, now that Spark shell has started, let's read our first data frame, which let's look at the path. So it is the gateway that we're calling from the DoK demo repository from the branch I just created, the daily ETL, and we'll read the Shopify collection. So now it sends a request to the S3A gateway, and I can read the data the same way my application, my Spark shell would read it from S3. And I have read successfully the collection. And now I want to partition it differently and save it to a different branch, to the same branch. So I'm writing the data partitioned by the event action, and the format that I'm going to use is Parquet. And again, right into the DoK demo repository under my daily ETL branch, but this time to the Shopify by action collection. Let's look at the uncommitted data for that branch. I could see that it is still running. And once it's finished, I can see the success message, success object would mean that Spark finished successfully. Now it's a point in time where I would like to commit to that branch. So I'm going to the uncommitted changes and commit, adding another partition. And I could also add any metadata fields that would help me later on to reproduce any issues I have. So using Spark 3.2.0 and commit changes to the branch. I could also go to the compare branch and compare between the branch I just committed to and main, and we see that the Shopify by action collection was added. If we go back and look only at the main branch, no changes were done to this branch. Any consumers are not exposed. It means that my experiment was in complete isolation. So let's go and merge that branch. And this is the first point in time where the data is exposed to external consumers of my production branch. So this was the demo, and this is all I had for today. I will share the slides and you could check out our docs or join our Slack channel and join the community, or simply starring our GitHub repository.
As always, definitely make sure you start the GitHub repo. Just a quick question is that in terms of how you're building this, we always ask a lot of our guests, were there any surprises along the way? Were there any things that were more challenging than perhaps you expected?
Yes, so there were many surprises along the way, like the story I told about the gateway.
Yes.
So we knew that it will hurt to scale LakeFS the way you scale S3, but we didn't imagine the amount of pushback that we will get from Spark, from the Spark or the data community. So we went ahead and implemented that quickly. We also started with a data model, which is more like MVCC and less like the way Git does things. And that also didn't scale very well. So we went ahead and changed that as well. There are probably a bunch of other
I'm sure.
surprises.
I'm sure. One of the things though is that we often ask as well too is that, when getting these technologies that previously, weren't Kubernetes native, let's say, onto Kubernetes, and Kubernetes is already its, a world of its own. One of the things we like to ask is like, if there's one thing that you could do to make, getting these technologies on Kubernetes easier, running data on Kubernetes, what would it be? If I'm saying you have one wish, you have a magic wand, one of the answers we find very often, or it seems to be the common one, are operators. Would you agree with that? Or would you think that you would hope to see other solutions in the near future to make running data on Kubernetes easier?
Well, I would say we invested a lot of efforts. So this, not just this demo, but anyone that wants to install LakeFS on top of Kubernetes would be as easy as we've just seen, right?
Yeah.
Just a single Helm chart to have everything running. I can't really say if operators are the easiest way. I can't really think of better alternatives than doing such, because it didn't start this way, right? We had few evolution in the ecosystem until we reached this point. But I think we're kind of in a good place right now.
Mm-hmm.
Doesn't mean that it can get any better.
Yep. No, that's true. I mean, and also when you consider how many of these things are being done for the first time, which is why our community exists. I completely understand that. Now, we also have another question that we're asking all of our guests. If you could have one person on your team, fictional or non-fictional, a superhero, a musician, anybody, to make this process just a little bit easier, a little bit more fun, who would that be and why?
Wow, that's a tricky question. I don't want to replace anyone in my team.
No, only adding, not replacing.
I don't have anyone specific in mind, so I would say you, Bart.
Oh, wow. Oh, I was not expecting that. Okay. That's the first time.
You can expect an offer after this.
You can talk to my manager. No, that's okay. Okay, that's good. No, it is true though also is that we often talk about, Kubernetes in general. Yes, it's a technical challenge, but it also should be solved with a people-based answer. You have a wonderful team at Treeverse. You mentioned about, your interactions with the Spark community were what they were, but it helped you have a better understanding of what to anticipate, the reactions and the feelings that were out there. Very, very good stuff. Now, you mentioned docs, you mentioned a couple of other things. Is there anything else that we should have folks know before we finish about anything else going on are you hiring in Treeverse in case anybody's looking for a job?
Yeah, we're hiring. We have many interesting challenges that we haven't yet fixed or implemented. So if anyone finds this talk interesting and want to learn more or even apply for anything, I'm available. You could DM me on the Slack channel. So go ahead.
Very easy to find. And like I said, this is the second talk that we've had with from someone from Treeverse. Very, very good content. If you can stop sharing your screen really quickly, Itai, so that I can share mine.
Sure.
So as always, while we are speaking here in the Zoom call and doing the live stream on YouTube, we have a very talented person who's behind the scenes creating something to represent all the different things that are being discussed inside the meetup in terms of the content being shared by our speaker. So whenever you get a chance, let me just, there we go. Okay, cool. No, I got you. Yep, you're fine. So while you were talking, our very talented graphic recorder, Anka, was behind the scenes doing an artistic interpretation of the different things that you were talking about. And there is very, very, very well covered, very consistent, very clean. As he mentioned, check out the GitHub repo. Go check out those docs. We'll be sharing the slides later on as well too, if you want to take a closer look. The demo, very, very straightforward and easy to follow along. So can't complain there. Itai, thank you very much for being with us today. It was an absolute pleasure.